This is just a video that's going to walk you through my workflow for designing a robot on Onshape, the browser-based CAD program, and then exporting that into a URDF straight into a ROS2 package and using Onshape-to-Robot, and then just walk you through what my workflow is following that to make that URDF Xacro enabled, split it into various modules, and ultimately to get it to a stage where I can launch it into a gazebo simulation and sort of drive it around with the teleop ROS2 run teleop twist keyboard. Now you can see the little robot I've designed here has got Lidar, which we can have a look at here. And you can see from the RViz simulation that it's got a camera attached to it as well, and the camera, if I just get rid of the Lidar for a moment, the camera is just on a little basic mount there at the front, and then you can see from here that we can sort of drive this around, and the camera is picking it up, what's in front of it, and you can also see obviously on RViz the Lidar is picking up as well the blocks that I've put in place on this custom world here. So let's close that, let's close that, we'll clear these because we'll be using them in a moment. So let's start with Onshape. Now what this video isn't going to be is an Onshape tutorial, because it would be very long. It's probably going to be quite long anyway, but it would be very long if it was. But there's a couple of things that I do need to show you that are very specific to Onshape-to-Robot, where you're exporting it for use in a ROS package. So here I've got my parts. So I've got my chassis, I've got my Lidar module, I've got my little camera mount, I've got my caster wheel frame, and I've got my caster wheel. And then of course I've got my actual wheels here as well. Now importantly for the parts, what you just got to make sure you do is assign a material to them. Now that's important because it's going to give them physical properties such as weight and inertia that's really important for a gazebo simulation. So do make sure that your individual parts that you have assigned sort of realistic materials to them. And then when you come to assemble the robot, what I've done here is I've assembled the Lidar and the camera mount affixed to the chassis using what's called fastened mates, and the wheels. So both the rear driven wheels and the frame for the caster wheel and the caster wheel itself, they are all mated to the chassis using what's called revolute mates. Now the really important thing to make sure you do is the way that you're naming the mates is really critical for when you're exporting using Onshape-to-Robot. And as you can see here, it doesn't matter what type of mate it is, all of them have this DOF underscore as the first 4 characters. So all of them have got DOF underscore and then a kind of a description of what the mate is. And that bit, obviously the description, you can do whatever you like, but you'll see DOF caster frame, DOF caster wheel, DOF right wheel, so on and so forth. Now what we're not going to do here is we don't need to export anything at this moment. We've done everything we need to with our assembly. The next stage is to get Onshape-to-Robot installed so we're able to use it. Now the steps for that are as follows. We're going to bring our terminals back. Now the first thing you need to do is create a Python environment on your machine. You can't install Onshape, well you can, but you shouldn't install Onshape-to-Robot system-wide. So the first thing you want to do is use this command, which is Python 3-m venv, so venv, and then whatever you want to name your environment. I've just called mine onshape_robot_emv. You can call it whatever you like. I'm not going to do this now because I've already done it, but what you'll end up with once you have done that, if I go to the home directory, you will see you've got your environment there. So once you've done that, what you then need to do is activate your environment, and that's very simple. You're going to go source, the name of your environment, then bin, and then activate. And once you do that, you can see up here to the left that the environment is activated. Now once you've got your environment activated, the next step is to install onshape-to-robot, and that's very simple using this command. So pip install onshape-to-robot, and I'll put all these commands in a helper file which I'll link to in the video description as well. Again, I've already installed it, so I'm not going to do it again. The other thing I would install whilst you're here is something called PyBullet. There's some great videos about onshape-to-robot on YouTube that kind of explain what PyBullet is and how it can be helpful. We won't be using it here, but you may as well install it at this point in time in case you need it in future. Now once you've done those two things, you can deactivate your environment. And then what we're going to do is we're going to hop back over to Onshape to do something very important, and that is we're going to come up here, we're going to go to My Account, and then we're going to go down here to Developer, and then you're going to click on API Keys, and you're going to generate a new API key and give it a name. Give it something like Onshape to Robot API Key. I'm going to call it API Key 2 because I've already got one. And then you're going to tick just these two boxes, that it can read your documents and that it can write to them. You're then going to create the API key, and what you're going to get is a key and a secret key, and you're going to need to make sure you save both of those. I will be deleting this this API key at the end of this video, obviously. So what we're going to then do is we're going to put those keys into this structure here. So we've got export, bring this back here, export onshape API equals https://cad.onshape.com, then export onshape_access_key equals, and then your key that you were just given, and then export onshape_secret_key equals, and then your secret key. And what you want to be doing with these is you are likely to have a if you're using ROS, you're going to be having in your .bashrc file in your home directory, you are likely to have some custom scripts, for example sourcing the ROS2 distribution, doing your colconr completes, and sourcing your workspaces. So I always have in my .bashrc file, I've always got some custom scripts, and what I would do is put these custom scripts at the bottom of your bashrc file. You only need to do it once they're in there. Every time you open a terminal or source your bashrc, you're going to be sourcing these really important things. So that's a critical step there. Now once you've done that, the next step is to actually create our ROS package. So let's now I keep all my ROS workspaces in a sort of parent directory called ROS workspaces. You might not, but this is what I do. From here what we're going to do is make a new directory, and let's just call this my robot workspace, and then we'll go into that and make an src file, and then we'll go into that, and from here we're going to create a package. So let's just call this so we'll do ROS2 pkg create, let's call it my robot description. I'm going to go build type ament cmake. So if I now check, you can see I've got the my robot description package, and if I go into it, what I'm going to have by default is obviously a cmake list and a package.xml, but you'll see I always have an include and an src file. I'm going to, with rm-rf, I'm going to remove the include and the src file, so I have no subdirectories. But now what I'm going to do is create a very important file in there that we're going to use. So I'm going to do touch my robot .config my robot config.json. I use gedit as for text editing, so I'm just going to do gedit myrobotconfig.json. You could open it up in a VS Code or whatever you like. I just find it easier to do it this way for this. So what that's done is that's opened up an empty file for me. And what I'm going to do is drop some pretty important stuff into it, which I'm going to walk you through in a second. So here is just a template that I use. So in your config.json file, the most important things that you've got to do is here up at the top. So you've got your document ID, package names, and then you've got some joint properties here, but we're going to come back to these because we have to do some messing around once we've done the export anyway. But the document ID, so if I go back to my Onshape, and let's go back into our robot that we've designed, and we've got our assembly here. Now up here in the URL you'll see a load of different codes, but the first one after documents, that is the document ID. So we need to copy that, and what we're going to do is we're going to paste it there. The next thing is the package name. Now we just created the package and we called it my robot description. The robot name, let's just call it my robot. And then the assembly name. Now the assembly name you can see here on this example, because this is one I've made for another package, is Slambot. But let's just rename this and call it my robot, like that. So we've got the assembly name correct. That's important because it needs that to find the correct one. So let's call that my robot. These settings we're going to keep the same, and again you'll find this in the helper file that I put in the description of the video. And then we've got our joint properties. Now if we go to the back to Onshape, where I said that we had these all important mates which I'd named in a certain way, what we can see in joint properties, we've got a default setting, and then we've got each DOF blah 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 section, and what you can see is DOF right wheel type revolute, DOF left wheel type revolute, DOF caster frame type revolute. This one, if you wanted to put limits on it, it's got limits. For a caster frame it probably wouldn't have, so I'm going to get rid of them in this case. Then we've got the caster wheel type revolute, and then we've got the Lidar and the camera mount, which were both fixed. So really important that we get those looking correct. So once I'm done with that, I'm going to save it, close it, come back to my terminal, and what you'll notice is I'm still in at the moment the my robot description package. So if I go ls, you can see we've got the CMake list, but the most important thing, we've got that my robot config.json file. So the next step is what we want to do is now reactivate the Python environment, and we can do that by doing source. We're not in the home directory, so we're going to need to do that, and then we're going to go onshape-robot env bin activate, and that's activated our Python environment. But you'll notice we're still in the my robot description package, which is critical, because the next step we're going to do now is onshape-to-robot, and then the name of that config file, which was myrobotconfig.json. Hit enter, and you can see it's now doing its thing, which I'll show you in a moment what it's done. But this is onshape-to-robot doing its work now. So it's just pulling out all the parts, adding them into our robot package. So next step is I'm going to deactivate. I don't need the Python environment open anymore. And what I'll do is go back a directory. So we're in the workspace src folder, and then I'm going to open VS Code now. So let's just bring this over here, clean it up a bit. It's going to possibly be a little bit small. Let's see if we can zoom in a bit. Zoom in, there we go. Okay, that's hopefully a bit easier to see. So in our robot description package, what you'll see now is we have an assets folder, and in that assets folder are all the parts that made up our assembly on Onshape. You'll also see there's our config.json file that we used. We're not going to need to use that again, but I just keep it there anyway. But you'll also see we've got this robot.urdf file that's been created, and that's where onshape-to-robot has done a lot of work for us in terms of pulling all the parts and the joints and having their sort of moments of inertia and their origins and their points in space. It's done a lot of heavy lifting for us. So we've made a lot of progress, but how do we get from this to being able to effectively launch our robot and run it in a gazebo simulation? Well, my first step here is I'm going to create some more directories. I'll do this via the terminal. So I'm going to go back into my robot description, where we can see we've now got assets directory and then our other files. I'm going to make some new directories. One is going to be called launch, one is going to be called URDF. I'm going to call one params, one worlds, one models, in case I have any custom models to go into custom worlds. And I'm going to have another one called rviz as well. So that you can see that's created some new directories. Now what I'm going to do is just go into the URDF directory, which has currently got nothing within it. And in here I'm going to make 3 directories. One's going to be called modules, one's going to be called gazebo, and one's going to be called Xacro properties. Again, you name these whatever you like, it's totally up to you. This is just my workflow. So that should now show us these. Next step is what I'm going to do is take the robot URDF and I'm going to put it in the URDF directory. And what I'm going to do is rename this my robot.urdf.xacro. From here, I'm going to be dragging some files over from another one I've worked on earlier, just to make things a little bit smoother, a little bit quicker. So from here, what I'm going to do is, firstly, we are going to, in the robot name where it's got my robot, is we're going to put the Xacro functionality in, like that. And the next thing I'm going to do is go to modules. Now, my assembly here is, it's got the chassis and the wheels, it's got the Lidar, and it's got the camera mount. So in the modules, what I'm going to do, and again, you break it up however you feel comfortable, but I'm going to create a file called chassis and wheels.xacro. I'm going to create another one which is going to be lidar.xacro, and I'm going to create another one called camera.xacro. And in each of these, what I'm going to do is take these top 4 lines, and I just need to close that robot tag. And what I'm going to do is take out the name. We don't need the robot name in the modules. We need it in the main file, but we don't need it in the modules. Now, for me, VS Code doesn't recognize it's XML. So if I come down here to plain text and just go auto detect, it'll then recognize it. So I'll take this, and my camera.xacro file will have that. My lidar.xacro file will have it. And then I'm also in my Xacro properties folder. I'm going to create a file in here called Xacro properties.xacro. And again, we'll just drop that in. And in my gazebo subdirectory, I'm going to have gazebo properties.xacro. Drop that in. And we're going to have Gazebo Plugins.xacro as well. And all of these, you can see I just have to do auto detect for VS Code to recognize that they are XML files, so bear with me whilst I just get those all recognized. Makes it a bit easier. Okay, so now let's start splitting this apart. So if we come into our myrobot.urdf file, what we're going to do first is I'm going to take the I've got the chassis link, the chassis part, the caster frame, the caster wheel. Here's the joint from the caster frame to the caster wheel. We've got the joint, which is the chassis to the caster frame. Then we've got the driven wheel joint, driven wheel 2, so that's the other wheel, and the joint, and then we'll come down to the camera. So I'm going to cut all of that away, and I'm going to drop all of that into here, into the chassis and wheels module. Now what I need to do is a little bit of sorting out here, because, and again, this is personal preference, but I find it much easier to name things a little bit differently. So whenever I have a link and a link name, I'm going to, onshape-to-robot will just take that as whatever the part name was. So I'm going to just change the name to chassis_link. Caster frame is a link, so I'm going to put underscore link there. Caster wheel is a link, so that's going to become caster wheel link. And then we've got a joint here. So the joint name at the moment, so this is the caster wheel to the caster frame. So it's just caster wheel at the moment, so I'm going to call it caster_wheel_joint. And then obviously our links now are caster frame link and caster wheel link. This is another joint. I'm going to call it caster frame joint, and this is chassis link and caster frame link. This is not, you don't need to necessarily do this. I'm doing this because it makes it easier. You don't have to. So here you'll see that it's called our link for the, I can see this is the right wheel, because if I come down here, I can see that the joint name is picked up right wheel. So I'm going to sort the naming out here as well, so so everything's nice and clear. So I'm going to change this from driven wheel to right wheel link. And then the joint name I'm going to call right wheel joint. And then that of course is now chassis link, and this is not driven wheel, it's right wheel link. I'm going to do the same here. This is going to become left wheel link, and this joint is going to be left wheel joint, and it's going to be from chassis link to left wheel link. Okay, there's a few more bits I need to sort here before we move on. I need to put this is a driven robot, and the origin currently sits at the bottom of the chassis, so I need to put a base footprint in. And again, I'm just going to take this from another example I've got. So I've got a link name of base footprint, and I've got a joint name which I just call base joint, and it's a fixed joint, and the parent link is the base footprint and the child is the chassis link. And all I've done here is, and you can do this, so on my Onshape model here, you can see that's the origin. So what I needed to work out was what's the distance from that to the ground where the wheels are. Now you can work that out going to your parts and measuring the distance from there to there, and then measuring the radius of the wheel. Again, it's beyond the scope of this video to go through all of that. And I can tell you that for this model it's 0.045 meters. So that's why I've put the z-axis as 0.045 meters, and that means that the base footprint will be on the ground, and when the robot's launched into RViz it won't be kind of sank into the ground. So that's the first thing we need to sort. Now the next thing that we need to sort is for any joints that are rotating like wheels, is we need to do a little bit of changing there, because Onshape-to-robot doesn't quite pull it off right. So if we go down, so the first joint we've got here is the caster wheel to the caster frame. Now what you'll see is that this is a joint type of revolute. ROS doesn't like that, so we're going to change that to continuous. So anywhere where we see a revolute joint, we're going to be changing that to continuous. So they're done. Now the other thing you'll notice is the onshape-to-robot export, it's put limits on the joints. Now obviously for certain things that would be realistic, but for wheels it can spin, so a caster frame and a caster wheel and the driven wheels, there shouldn't be any limits to how much they can turn around. So what I'm going to do here is remove the lower and upper limits completely. Again, this is the caster frame to the chassis. Well, a caster frame should be able to spin around freely, so I'll remove the limits there as well. Then we've got the right wheel and the right wheel joint. We've already changed that to continuous, but I'm going to remove those limits as well. And then we've got the left wheel joint. We've changed that to continuous, but we're going to remove those limits there as well. So that's all sorted now. So the next stage is to come back here and we're going to do our camera now. So we want the links and the joints, so we'll cut those and we will go to camera and we're going to place them into here. Now again, I'm going to do a bit of sorting, so that's link name camera. So I'm going to call that camera mount link. Again, you do what you like. This is just, I find this more helpful. And then the joint name is going to become camera mount joint. This is fine as a fixed joint because it doesn't move. And then the parent link is the chassis link and the child link is the camera mount link. Make sure I get those typed right. Okay, now for the camera, there is a little bit of additional code we're going to put in here. And this is to make sure that the camera works on RViz, and also if you're going to use OpenCV, you want to be including this. Is actually, if you go on, there's a ROS page all about this. But what you see here is we've got the camera optical link, the camera optical joint, and the parent link is the camera mount link, and the child link is the camera optical link. So that is absolutely fine like that. Now we may have to mess around with the way that the camera mount is oriented, but we're gonna, when we open up RViz, we're gonna get a feeling for whether our camera's pointing the right way. Now because I've done this before, I know that this needs to be 0, 0, 0. Okay, so that's that one all done. And then if we come back to our main robot URDF file, you see what we've got left here is the Lidar related links. So we're going to cut those out and we're going to pop these in the Lidar module. And we're going to call this Lidar link. And this is going to be Lidar joint. And the parent link is chassis link. And the child link is Lidar link. And that's all we need to do on that one. Now, let's move over to Xacro properties. What I'm going to do here, the only thing I need to do here is this, and you'll see why when we come to the Gazebo plugins. Again, this is, you don't have to do this. This is just what I choose to do because it makes things nice and modular. Now obviously this is my robot description, that's the package name, and the robot name is my robot. So I'll save that. And then we come to the Gazebo plugins. Now there's loads of different ways you can do these. Again, this isn't really a video on how all the Gazebo plugins for Diff-Drive robots and stuff work. So I'm going to try to avoid kind of going into too much detail here. If you go onto my GitHub, you'll find plenty of robots that I've set up where you can get all of this stuff and just copy it and use it. But basically we've got the Diff-Drive plugin, and now what we need to do is the joints. Now we've already named the joints correctly here, left wheel joint and right wheel joint. The wheel separation, now again this is where you would come to your robot on shape, and you basically need to measure from there to there. It doesn't have to be super accurate, you know, for example for this you could just measure from that face to that face. It's going to be close enough, but that's it pretty much exact for this robot. And then you need to put the real wheel radius in as well. These are all in meters, as you can see. And then here you can see we've got the frame ID and the child frame ID. Now this is why we've done the Xacro properties file, because that's going to be taking these properties. So that's quite important. It means you can basically, this is modular, you can use it for any robot if you do it this way. We've then got the joint state publisher, so I've got the left and the right wheel joint. Because I'm using sensors, you need to put this this plugin here. Again, pull my stuff down from GitHub and you'll get all of this. And then we've got the Lidar related stuff. So we've got the Gazebo references, the Lidar link, sensor name, you can call it whatever you like. I just call it GPU Lidar, and again it's relative to the Lidar link. I'm not doing vertical here, so I've just got the horizontal, and there's various settings you can sort of play around with there. And then we've got the camera sensor. So camera mount link, which is what we've already set our camera links to. So again, don't want to walk you all the way through this. Go to my GitHub, you'll be able to pull it all down and modify it for your own purposes. So next, what we want to do is just sort the gazebo properties. So again, copying from another example I've got open on my other screen. But basically what I'm doing is just giving some friction coefficients for the solid parts. And then what I'm doing is giving high friction coefficients for the driven wheels, a little bit of spring stiffness and damping coefficient. You don't really need to put them in if it's just a basic simulation. Caster wheel, I've done a pretty high friction coefficient, and then for the actual frame that rotates in the chassis, I've put a very low friction coefficient there. Again, you can play with all of those to get slightly different behaviours within the simulation. So, final thing we need to do then is in our myrobot.urdf is we need to include all these various files. So again, one I worked on earlier, so I can just copy and paste it in. But what we've got here is Xacro include file name, got Xacro properties, modules, the chassis and the wheels, the camera and the Lidar, the Gazebo plugins and the Gazebo properties. And then I can hit save. And that now is all lovely and modular and Xacro enabled and all set up and ready to go. So what have we got left? Well, we've got no custom worlds yet. That doesn't matter, we'll sort that soon. Easiest way to do that is actually to launch into an empty Gazebo simulation first. We've got no RViz config. Again, easier to just launch into RViz without any config, get your config right, and then save your config file. So we'll do that in a moment as well. Now we've got a params folder in here. What we need to do is create a Gazebo bridge.yaml file. And if ever you're using sensors or controllers, plugins, you need to create a Gazebo to ROS bridge. That's a whole topic in itself, and again, this you can get off my GitHub package and just amend it to your own needs. The only thing I need to do here is our robot is not called Slambot, it's called my robot. So I'm just going to, wherever I see Slambot here, because this is one I used on another one, I'm just going to change that to the actual name of our robot. I think that's it. Yeah, that looks good, so I can save that. And then we've got models. We're not using any custom Gazebo models here, so that'll stay empty on this video. And then we've got our launch files. So let's create some launch files so we can have a play with this. So first launch file I'm going to do, I'm just going to call it rviz rviz.launch.py. and then I'll do a gazebo empty.launch.py, and then a gazebo custom.launch.py. That's what I usually do. Let's start with the RViz launch, and again I'm going to take a sort of template launch file that I use. You please feel free to go into my GitHub and pull it and use it yourself. So up here we're going to change these to our specific package. So this is my robot description there as well, and the URDF file is myrobot.urdf.xacro, and then we don't have a RViz config file yet, so I'm just going to comment that out for now. Everything else is fine. The only thing I'm going to do here is we're not using a custom RViz config file at the moment, so I'm just going to comment that section out. And where we launch RViz, I'm just going to comment out the arguments section here because we're not using this custom RViz config file yet. And then I'm going to just comment that out as well. So before we do the gazebo ones, let's just try and build and launch this and see what problems we get. So let's go back to our workspace, and I'm just going to do a colcon build. That built okay, which is good. I am just going to edit my bash RC because I just need to make sure that I source the right workspace here. So bear with me, I'm just doing this on another screen. So it was my robot workspace, WS. So, okay. So now if I source the bash RC, that should source the correct workspace. And let's give it a whirl. So we'll go ROS2 launch, my robot description, that's a good start. And then let's go RViz. Aha, it's not working, and I know exactly why. So a couple of files we forgot to edit. One was the CMake list file. So what we need to do is we need to get rid of all of that and put the install tag here, and we've got launch, yep, we've got assets. So these are all the directories, URDF, params, worlds, RViz and models. And then the package XML, I'm just going to put some dependencies in. So we've got the joint state publisher, the robot state publisher, Xacro, the ROS2 Gazebo, Sim and Bridge, and RViz 2. We'll save those as well. So let's do another colcon build, source the bash RC again, and give this another go. So my robot description, and hopefully this time that looks a bit more promising. So if we hit launch, this should chuck up RViz for us, which it has. And what we're going to see at the moment is not a lot, and that's because we need to sort a few bits first. So first thing I'm going to do is add the robot model, and I'm going to add the TF as well. And then what we're going to do is we're going to change from map to base footprint. That's going to sort our global status. You can see we can't see our robot model yet, but that's because if we come down here and we want to select the topic, which is going to be robot description, and we're sort of seeing something now, and the reason we're not seeing it fully is because we need to put the robot model name here in the TF prefix, and that should, let's see why that's not TF prefix my robot. So if I just come back to our Xacro properties, value my robot, and that should, let's just have a look at our Gazebo plugins, robot name, So it's still picking up a slam bot, so let's see why it's doing that. It means I've left something somewhere. I think I know why. If I go to my RViz launch file, I forgot to change the name of the robot. So let's start again there. So kill that, colcon build again, resource of bash RC, relaunch, and we should have success this time. Okay, right, so fixed frame, we're going to go to base footprint, and we're going to add robot model, we're going to add TF, and if we go to robot model this time, we should find that we select the robot description and then the TF prefix if we put down as my robot, and that's looking better. So we've got our robot showing nicely there. The TF all looks okay. I'm just going to hide the TF for now so we can see the robot there. Now one thing I want to show you is if we check the caster wheel joint first, so we're not going to see it moving because it's impossible to visualize, but you can see there working fine. Now if I do that, you see the right wheel's moving backwards when I move it there, whereas the left wheel is moving forward. Don't know whether you can see that, but that's going to give us a problem, so that's something that we need to have a quick look at, and it's a very easy fix. So let's close this and let's go back to our URDF setup and to our chassis and wheels, and what we need to do is find the right wheel joint, and we need to swap the Z-axis on its head basically. So we're going to change that from 1 to -1. So we should see now that the right wheel joint's Z-axis is -1 and the left wheel joint is 1. So let's come back here, do a colcon build again, source, and launch into our viz. And let's just get our setup sorted again. Base footprint will be our frame that we're operating from, and then we're going to add the robot model, and we're going to add the TF, and the robot model we need to pick up the robot description topic, and then we need to put the prefix in, and that's looking good. And then if we hide the TF and we'll just do a quick test on that right wheel, that's now moving forward. That left wheel is moving forward as well, so that's perfect. Now what I'm going to do really importantly here is file, save config as, and let's go into our workspace, my robot description, and I'm going to go RViz, and I'm going to call this my robot RViz only .rviz and save. I'll close that, and then if I come back to, let's close some of these folders that we some of these files that we don't need at the moment. If I come back then to the RViz launch file, I can now reintroduce this custom RViz file. Now we obviously need to get the name right. It was my robot RViz only. I'm going to uncomment this because we want this now to be used, and then I'm going to uncomment the arguments so it's actually using it when it launches RViz, and then I'm just going to uncomment that as well. Do a colcon build again and relaunch, and what we should find is RViz now opens as we expect it to. So that's step 1 done. We can now launch our robot into RViz, which is great, and we can check all the TFs and just check everything's behaving as we expect it to, really, which it appears to be. So let's close this and let's get this launching into Gazebo now, into an empty world. So again, I'm not going to walk you through this whole file because there's a lot involved here, but what we're going to do is same edits we did last time. So my robot description for the package name, Remember to do this time around, change the robot name. That's also my robot. Now RViz config, we haven't got one specifically for when we're using Gazebo as well. So for now, what I'm going to just use is the one we just created for RViz only. And we haven't got any custom worlds or anything here because we've just got an empty world we're launching into. Now the rest of this you now don't need to touch. If you use my launch file, this is all now perfectly ready to go. So if I save that, do another Colcon build, resource the environment, and this time we're going to, instead of the RViz launch, we're going to do the Gazebo empty launch. And RViz launches. Now we do get a TF error, and the reason for that is we are no longer using the joint state publisher. We're using the Diff-Drive controller, and the Diff-Drive controller is not doing anything with that caster wheel at the front. So from an RViz standpoint, it's sort of thinking that it's picking up an error there, but that is not really important at this point in time. The main thing that we want to do here is make sure that we can get the Lidar and the camera showing on RViz. So what I'm going to do is add, and I'm not going to choose camera, I need image. And I'm going to add laser scan as well. Now if I go down to image, I've got an error at the moment, and that's just because we need to get the image topic, which is camera image raw. And you can see we are now looking out to an empty Gazebo world, so that's working. If I go to laser scan, again it's topic related, the error, so if I go scan, that is now working fine, and I can see the messages coming in. Now obviously there's nothing in this world, so it's not picking anything up, but that is working as we expect it. I tend to pop the image over there. So we'll try and bring that back. Let's remove that and do it again because I lost it. Image topic. Right, let's try this again. There we go. Pop it there, and then we can see it a bit better. So before I close this, I'm going to save this config as. You'll see it tries to save it in the install file. We don't want that. We need to come back here and go to the source file, go to RViz, and let's call it, instead of RViz only, we'll call this Gazebo. We can now close this. I'm going to come up to my empty Gazebo empty launch file, and we'll just change our RViz config to Gazebo. And that just means it'll open up correctly next time we come to use it. Okay, so final thing I'm going to do now is just create a one that just launches it into a custom world. So I'm going to do a quick Colcon build because we have changed that config file for RViz. I'm going to launch into the empty world again, and we can see our robot there. Now we can drive it around at this point because we've done the necessary plugins. So if I go ROS2 run teleop keyboard, and if I zoom out a bit so we can see that we can drive this robot around, which is pretty cool. Not a lot to do in this world, but if you can see, because we've set the caster wheel up correctly, you can see that the caster wheel behaves as it should. So if I just try and spin this on its axis, you can see the caster wheel turning around. It's behaving exactly as you would expect it to. and that's because we've done it as a joint with no resistance. And a lot of the time when people are doing robots like this in simulation, they just put a frictionless ball at the front, and that's fine. I quite like just doing it with an actual caster wheel. It's up to you. Right, let's whilst we've got our gazebo world open in front of us, what we're going to do is, I've moved the robot around, so I think the easiest thing for me to do here is close that and just relaunch it again, just so we know exactly where the robot launches into. And let's just keep it simple, and we just put a few objects around. And again, you can launch into custom worlds with mazes or models, and I've got actually some other videos on that as well. But this, just keeping this super simple. So I've put some stuff in the world. Now what I need to make sure I do critical is remove the robot. So I've just got the world, and then I can go save world as, browse, and again we'll come to our robot workspace, go to the source folder, go to the robot description, and here in worlds I'm just going to call this my custom world.sdf, and save, and OK, and then close that. And if we come back to VS Code, we should have our world there. So now the final thing I'm going to do is create our custom world launch file. And again, just need to make a few changes because I've just pulled this across from another package that I've built. So that's going to be my robot. That is going to be my robot. That's my robot. That's my robot. That is my robot config. Let's see how we named that. We just called that my robot gazebo.rviz. And then I think we called it my custom world. So change all those, and that should be everything you need to do on this. Just double check that all looks good. Save that, and Colcon build, source, and then we'll launch. And this time we're going to launch into the into the custom world. And everything is looking good so far. We've got the image. For some reason the image panel's disappeared on me. I'll sort that in a moment. I must have caused that with the config file. I've saved the wrong one or something, but we'll sort that in a moment so we can get that image in front of us. But what we can see here is we've got some Lidar scans showing now, which is pretty cool. And let's just remove this file, add image, and let's get that topic. Yeah, and we've got our image there as well. For some reason me moving it over there seems to have caused a problem with it. So what I'm just going to do now I've got this config sorted is just save the config. Again, remember it's going to try and put it in your install directory, so you've got to come back here, go to your source directory, and we'll just save it over that. That should sort that for next time around. Now we can drive our robot around our custom world. So let's have a go. So there it is, moving around, and you can see the image on our viz. The camera is also picking up what's around us, and you can see the robot behaving as we expect it to in Gazebo as well. So that is the workflow to start with a robot that you've designed on Onshape, to bring it off Onshape into a ROS2 package using onshape-to-robot, and then my workflow for turning that into a proper robot description package with Xacro and Gazebo plugins, etc, etc. As I've said a number of times throughout this video, you can go to my GitHub. I'll put the link to the GitHub repository in the video. But it's GitHub benmay100, and from there you'll see there's quite a few robot description packages that I've created that have this kind of setup. So you can get everything you need from there, the Gazebo bridge, how I structure the URDF files, you can get my launch files, you can get everything that we've gone through from there. And please use it and edit it and amend it to do whatever you need it to do. Thank you for watching.